In the previous lecture we were discussing about the expression for the stream function which you see in the board behind me, how to derive that for flow, low Reynolds number flow past a sphere. Now given this, our objective is not just this is a pure mathematical expression, but we require to use this expression to calculate the drag force. We will systematically see that how using this expression for stream function we can calculate the drag force. So the steps are very logical and start with obtaining expressions for Vr and V theta. So Vr is 1 by r square into 1 by sin theta this is the definition of Vr as a function of psi. So 1 by r square into del psi del theta into this term in the box, right. So this sin theta gets cancelled, this 2 gets cancelled, even this r square gets cancelled. So u infinity cos theta Similarly, you have an expression for V theta. Minus 1 by r sin theta derivative of this function with respect to r. So this will be 2r minus 3 by 2 r plus right no r, sorry, just 3 by 2. So this is r, sorry, capital R, right. So this is all right, plus, so there will be minus here 1 by r will become 1 by r square. So minus r cube by 2 r square, right. So you will have these cancelled. So minus u infinity sin theta you can take these 2 r inside, 1 minus 3 by 4 capital R by small r minus r cube by 4 r cube. Okay. So, very nice expressions for Vr and V theta. Now, to calculate the drag force, what you require? You require the stress distribution on the sphere. The stress has 2 components, one is the hydrostatic component, another is the deviatoric component. For the hydrostatic component, you have to find out what is the pressure distribution around the sphere. So, how will you get the pressure distribution? You will get the pressure distribution if you substitute these velocities in the momentum equation, because momentum equation has both velocity and pressure gradient. So, let us do that. So, let me write the momentum equation, the R momentum equation. So, these forms are very cumbersome for the polar coordinate system. Again I am telling, never try to remember these. See, although this is a part of the derivation that we are doing in the class, if in the exam somehow these are required, these portions will be given, that is the momentum equations in this polar coordinate system. So, that should not be a deterrent. Okay. These forms are so cumbersome, even if you write by seeing, there can be a mistake. So, I mean no great glory in memorizing. So, then I am just telling you the strategy, because I do not want to waste time in calculating these individual terms, right. You know Vr and V theta, you just differentiate this. These derivatives are straightforward. So, once you differentiate this, that is you get Vr and V theta from here. So, if you put all these expressions for Vr, V theta, their derivatives, then this will be the final expression 1 by mu when it gets remarkably simplified after putting everything together, and this is the form that you get. So, you will have P, if you integrate this, u infinity cos theta. So, there is a mu u infinity cos theta 3r, then r to the power minus 3 dr is r to the power minus 2 by minus 2, right. So, there is a minus plus a constant. How do you, what is that constant? From intuition you can tell, okay, if you put this constant, then what is the condition here, that at first stream at small r tends to infinity, you have P equal to P infinity, which is the ambient pressure. So, if small r tends to infinity, P equal to P infinity, then this is also P infinity. So, I am writing in one step. You can have an interest to see if the theta momentum equation also leads to the same P. So, the theta momentum equation, and it should, I mean it is a cross check just to make sure that all the correction calculations are done correctly. Theta momentum equation is also equally cumbersome. So, minus 1 by mu r. See, vector forms, that is why they are so compact and nice. If you write these, those they look very elegant, but if you want to really do this algebra, then you have to open up the vector form and I mean bring out, like in every human being there is a very beautiful outside and there is very ugly inside, and that ugly inside opens up when you open up from the vector form to this, you know, nasty form. So, okay. So, again the strategy is very similar, you substitute the expressions for Vr and V theta and then you come up with this. So, you come up with so, if you integrate this, this will lead to the same expression, okay. Sin theta integration will become minus cos theta. So, it will be the same. So, getting the pressure means you know the hydrostatic stress distribution. How do you get the deviatoric stress? The deviatoric stress you have to appeal to the Newton's law of viscosity. So, the deviatoric stress so tau r deviatoric is equal to 2 mu, this is the deviatoric part only, the total tau r is deviatoric minus this P which is hydrostatic. So, 2 mu del V r del r, this is like tau equal to mu du dy expressed in, you know, this coordinate system. So, this will be equal to 2 mu u infinity cos theta tau r theta, this has only hydrostatic deviatory component, this does not have any hydrostatic because it is shear stress. So its formula is mu So this is viscous normal stress. As I told earlier that viscosity also may give rise to normal stress. So this is viscous normal stress, this is viscous shear stress. So if you put all these, this will become minus 3 mu u infinity r cube sin theta by 2 r to the power 4. Again substituting v theta Vr and doing the derivative part. So now we have all the ingredients to cook the food, and that is what we will do now. So what is the physical picture? You have the sphere, you want to calculate the drag force. The drag force is clearly a function of r and theta. Why? Because the stresses are also functions of r and theta. So what we will do is, at an angle theta we will consider a small element d theta and take this element along the sphere. So on this small element, what is the normal stress? Tau r deviatoric minus p. Okay. And what is the shear stress? Tau r theta. So what is the drag force? Drag force is defined as the flow in the force in the direction of the relative flow. So the relative flow is in this direction. So we have to resolve the force in the direction of the flow. So what is that? Remember, these are not forces, these are stresses. So that has to be multiplied with a suitable area that we will come up with. So tau r deviatoric minus p into what? Cos theta, right? Minus tau r theta sin theta. So this is in the forward direction, its sin theta is in the backward direction. So minus integrate, what is the area on which it is acting? This is r sin theta, this is r d theta. So the surface area of this is 2 pi r sin theta into r d theta, 2 pi r h. So 2 pi r sin theta into r d theta. Remember, this is evaluated at small r is equal to capital R. The drag force is on the sphere, and what will be the limit of integration? Yes, it is not 0 to 2 pi because already 2 halves are covered by one element. So it will be 0 to pi. Okay. So from here you go to the other side, from theta equal to 0 to theta equal to pi, in this way the full sphere is covered, right, because this bottom half is already covered. the expression for P, let us rewrite, I have erased it from the board. So, P is P infinity minus 3 mu u infinity r cos theta by 2 r square. Okay. So, let us now put all this. Tau r deviatoric is 2 mu u infinity cos theta. If you put r equal to small r equal to capital R, then you divide by r into 3 by 2 minus 3 by 2. So, that is 0, right. Minus P cos theta. So, minus P cos theta is minus P infinity cos theta plus 3 mu u infinity by 2 r cos square theta, right. And then there is another term minus tau r theta sin theta. So, that minus and this minus will make it plus. So, 3 mu u infinity by 2 r sin square theta, integral 0 to pi into 2 pi r square sin theta d theta. So, the first thing is that this is 0, this does not appear, and again I repeatedly tell in my classes, see, ignorance is a blessing. Some people have an idea that viscous effect do not give rise to any normal stress. So, then they will not consider this term. By grace of God, this term is 0. So, even if there is this ignorance, that ignorance will not reflect in any error in the calculation. Can you tell what will be the contribution of this P infinity cos theta? See, by integration all of you can tell. See, where from this comes? P infinity is a uniform pressure which is integrated over a spherical body. So, the net effect will be 0. You can check with this integral cos theta sin theta d theta 0 to pi, that will be 0, but it is also from the physical understanding. And then you see remarkably 3 mu u infinity by 2 r, you have this cos square theta plus sin square theta. So, algebra, geometry, trigonometry, all the things that we have learnt in school are appearing in this exercise. So, 3 mu u infinity by 2 r into 2 pi r square sin theta d theta, right. So, these 2 gets cancelled, this r gets cancelled. So, sin theta d theta is minus cos theta, right. So, 3 mu u infinity pi r minus cos theta between 0 to pi, cos pi is minus 1 and cos 0 is 1. So, this brings you to the famous Stokes law, 6 pi mu u infinity r. Okay. So, this is the force exerted by the fluid on the sphere. By Newton's third law, the sphere exerts equal and opposite force on the fluid, and that is how the fluid is so called dragged. So, one of the key issues in the Stokes law is that we have neglected the inertial term. That is one of the major assumptions. Otherwise, this is a very classical expression. So, we have to check what is the validity of this expression. So, we would put a question mark and make a short discussion on the validity of the Stokes law. So, the validity is dependent on Reynolds number, and instead of looking into the Reynolds number, we will see what is the inertia force and what is the viscous force. So, inertia force, just take one of the terms in the order of the inertia force. So, inertia force, these are all force per unit volume which are coming in the Navier-Stokes equation. This is rho Vr into, this is one of the terms in the Navier-Stokes equation, you will see one of the inertial terms. So, let us look into the expression for Vr and V theta. So, if you look into the leading order, so Vr leading order is u infinity and V theta leading order is of the order of u infinity into capital R by small r, that is the leading order term, right, u infinity into capital R by small r. See, this is order of magnitude, so whether 3/4, 3/2, all those things are not mattering. So, u infinity into capital R by small r, when differentiated with respect to small r, it will become of the order of this, right. This is the inertia force per unit volume. What is the viscous force per unit volume? So, this is one of the order of magnitudes. Okay. You can use also a tau r theta, but just as an example. So, remember in the Cartesian system, in the index notation, the stress tensor is del tau ij del xj. So, here that del xj becomes r. Okay. So, when you differentiate this with respect to r, it becomes of the order of mu u infinity r by r cube. So, inertia by viscous, of the order of rho u infinity square r by r square into r cube by mu u infinity r, right. So, you can write it in terms of Reynolds number, this becomes r, one of the r goes away, one of the u infinity goes away. So, this you can write rho u infinity r by mu into small r by capital R, okay, just multiplying and dividing by this. So, this is Reynolds number based on capital R. Yes. So, what we can conclude out of this, that even if the Reynolds number is small, inertia force may be much important as compared to the viscous force if small r is much larger than capital R, that is far away from the sphere. You can argue that I am calculating drag force on the sphere, so why far away from the sphere what is happening is important? This is a wrong argument, because the velocity profile that you have derived is based on the assumption that far away, not far away, everywhere the inertial forces are 0. But if far away the inertial forces are not 0, then the velocity profile will be different, therefore the calculations of tau r, tau r theta all will be different. So, although the calculation is on the surface of the sphere, it is on the basis of a velocity profile which is derived from the consideration of 0 inertia force. So, this matter was highlighted by one mathematician called as Osin, who gave correction to the Stokes formula. So, there are many corrections to the Stokes law in the research literature. In this course it is not very important to make yourself familiar with all those corrections, but you have to realize at least that the Stokes law has its own limitations. So, other than the major assumptions of unbounded flow and Newtonian fluid, the consideration itself of 0 inertia force becomes questionable if you have a situation where you are having a correction in the velocity profile which will be dependent on the inertia force itself, that cannot be neglected. Okay. So, with all these let us end this lecture, and so to recapitulate, what we have studied so far is mainly a collection of steady flow low Reynolds number problems, that is what we have studied, but there are many interesting low Reynolds number problems for unsteady flows, and we will look into those low Reynolds number unsteady flow problems which are very important for microfluidic applications in our subsequent lectures. Thank you.